This is Bernard Paulson, and this is lecture 8 from chapter 8 of the book. This is also the second lecture in part 2 of the book and this class. In lecture 7, we talked about how to get numerical values for the rate constants that appear in the rate laws and other numerical values we need. In this lecture, we will talk about some of the biological properties that characterize the stoichiometric matrix and therefore set some of the characteristics of biological networks. We will talk about a few topics in this lecture. First, we will talk about cofactors and carriers and what these molecules are, broadly speaking. These are all the, quote, site reactants, unquote, that appear in reactions. They are much more important to the integrated function of metabolism than one would assume based on a typical biochemistry textbook. I wish to talk a little bit about the consequences of bilinearity of chemical reactions when it comes to looking at network functions. I'll briefly also discuss the pathway view of a network map and a cofactor-based view. Then I will start to talk about how to build dynamic models step by step or module by module. I will first talk about the basic motif of energy transduction amongst the adenosine phosphates. This system was already introduced in the second lecture. I will then take that motif and couple it to a prototypic pathway. A prototypic pathway is one that follows the general structure of actual metabolic pathways. In part 3 of this book, lecture 10 and beyond, we will look at actual biochemical pathways. Here we will stick with prototypic versions to extract some concepts and features. First, we will talk about cofactors and carriers. So the notion of a cofactor or a coenzyme is shown in this slide. We see in row 1 in this figure an enzyme with its active site open. It then gets loaded with that pinkish and yellowish substrate. Once they are both bound to the pocket, there is a group transfer from the pink molecule to the yellowish molecule. And that group is indicated by the open circle. The types of chemical groups transferred will be described on the next slide. After the transfer takes place, both molecules are released from the substrate and another reaction can be catalyzed. In row 2, we see a slight variation of this theme, and in this case, the coenzyme or the cofactor molecule is tied to the active site of the enzyme and stays in it. This is indicated by that little black tether at the bottom of the active site. The substrate binds, the group transfer takes place, the substrate is removed, and now that group sticks to the coenzyme that in this case is called a prosthetic group that stays physically with the enzyme. Here are some examples of coenzyme and carrier molecules given in the first column, and the second column indicate which group is being transferred, and the third column shows that many of these basic cofactors are indeed essential vitamins. These are micronutrients, but extraordinarily important to the proper functioning of enzymes and metabolic processes. The groups being transferred can be chemical, methyl groups, acyl groups, amino groups, high energy phosphate bonds, protons, and electrons. In this class, we will be focusing on the adenosine nucleotide as a carrier of high energy phosphate bonds. We will also talk about NAD and NADP as carriers of hydrogen and redox equivalents. And as a third example in this table, we can focus in on the familiar heme prosthetic groups that sits in the cytochromes or in hemoglobin, and typically chelates an ion in the ferrous state or the +2 state that confers on it certain chemical activities. Here are some actual examples of these micronutrients. My favorite is given at the bottom, which is B12. Vitamin B12 is the most complex metabolite in metabolism. In organisms like E. coli, something like 3 to 5% of the genes are devoted to the biosynthetic pathway for this moiety, and it's only found in 3 or 4 enzymes, as I recall, in E. coli metabolism. A very, very expensive molecule to make and use. Here are more examples of vitamins that also are important for proper metabolic functions to take place. And I put this in here to remind students that their parents constantly urge them to take their vitamins. And that is not without reason. Most of these molecules carry critical functions in metabolism, and low levels of them in the body reduce the activity of all sorts of physiological processes. So take your vitamins. Now, that is a little bit of a biochemistry and a little bit of a background on prosthetic groups and cofactors. What we will do now is to start to look at the systems aspects of their function and begin to look at some engineering, or maybe more precisely, bioengineering quantities that are related to them. The motif that is shown in this slide is a generic one. Here we are looking at the moiety A that was previously symbolized by an open circle. It is being transferred from a donor molecule X to the carrier molecule C that can pick up this property A, and then it is given to an acceptor molecule that picks up A. The fact we have a carrier molecule decouples X from Y, and you don't have to have direct transfer of A between them. And we can also have a variety of X's and a variety of Y's focused on a carrier molecule. One of the most highly connected carrier molecule is ATP that carries the high energy phosphate bond. And there is a number of reactions that produce ATP from ADP. And there are many, many, many more acceptors of that high energy phosphate bond. I have noted earlier that the time scale associated with this conversion of this cofactor between a charged and a discharged state is about a minute, and that represents the master timescale of chemical energy exchange in metabolism. Note that the carrier cycles back and forth, back and forth. It is a cycle, if you will, like a conveyor belt that goes around and around. Briefly, I want to contrast the pathway view of a network versus maps we can draw that focus on the cofactors themselves. Here is a classical network map that conveys a pathway view. This is a tracing of redox equivalents through glycolysis, the familiar pentose pathway, the fermentation reactions that lead to various fermentation products being secreted, or alternatively, the anaplerotic reactions that take mass into the TCA cycle that spins around and around, makes NADH that drops its electrons, or its redox equivalents, I should say, onto the electron transport chain, where they're ultimately transferred to oxygen. At the top of the map, we show the transhydrogenase that can exchange redox equivalents between the NAD and the NADH carriers of redox potential. Some of the very, very key processes that take place inside cells are shown in here, including the ATP synthase that lets protons across the membrane and synthesizes ATP in doing so. This would be considered a classical point of view of a metabolic pathway or a metabolic network. And in this case, if you have good eyes and can look at the symbols, traces the flow of redox equivalents through these pathways and gives the redox equivalents of every metabolite as they are being given up onto the cofactors in these various pathways. Glucose, the starting molecule to the top left, starts out with 12 redox equivalents, and eventually they can all be transferred to ATP. A different view of the same process is shown here, where furthest to the left we have oxidation of metabolites to give up the redox equivalents. We have the primary redox carriers that pick this up, and there are three of them shown here: NADH, NADPH, and FADH. We also see the exchange by the transhydrogenase between the NADH and the NADPH forms. Then to the right at the bottom, we see a redox load that can pick up these redox equivalents, or they can be used to displace a proton across the membrane, and then as that proton is let back across the membrane through the ATP synthase, ATP is made. As I stated earlier, each one of these pairs represents a cyclic process where things are going back and forth, and thus we can look at all these cofactor pairs as a tangle of cycles through which redox equivalents are processed. This point of view is more of a systems point of view or a bioengineering point of view of a metabolic network. It is to be contrasted with the more familiar biochemical point of view given in the earlier slide. I will now begin to show how complex simulators are built in a step-by-step fashion. I will focus on the familiar motif from Lecture 2 that is focused on the exchange of high-energy phosphate groups amongst the adenosine nucleotides. That schema that we saw earlier is shown to the top left in this diagram. where you have the load on ATP as the top arrow producing ADP, and then the reverse process that builds ATP from ADP, and then the double-headed arrow reaction, that is the rapid kinase that exchanges, or I should say redistributes the phosphate bonds amongst the different forms. And then of course the basic carrier, the adenosine monophosphate, is synthesized and degraded. To the right I have a pictorial representation of the same thing, where the blue box represents the AMP molecule coming and going, and the decoration of it with the high energy bonds is shown by the red circles attached to it. So you can take a blue box and attach one or two high energy phosphate bonds. The detailed chemical view is shown in panel B, where we show ATP with 3 phosphate groups, ADP with 2, and AMP with 1. And AMP with this 1 phosphate is a part of the blue box pictured to the right. It is not a high energy phosphate bond. We talked about the capacity to carry high energy bonds, which is basically the summation of all the blue boxes, regardless of in which molecule they are found. And the occupancy is basically the counting of the red circles that decorate the blue box. So we have the capacity of this carrier to carry high energy phosphate bonds, and then how that is occupied by high energy bonds. And finally, to the bottom right, we show the ratio of the two as the charge. This is literally analogous to a battery that has a certain capacity that can be occupied by electrons, and you ratio these things out and you get the charge. These are the two pools we introduced in chapter 2, and the ratio between the two of them is the charge, and this is now more a functional or an engineering type parameters that one can use to interpret metabolic states. We will now go through a couple of iterations on building a dynamic model for this basic motif. First, I am going to close off that dashed red box and consider no inputs and no outputs and basically put them to 0. The mass balance, the dynamic mass balance for ATP would have a negative rate of usage, a positive rate of formation, and we have a positive rate of distribution, as I will consider the distribution reaction to be positive going from right to left in this diagram, and that is indicated by the plus and minus sign above that reaction. I could have defined positive direction from left to right, in which case I would have a negative sign in front of the V distribution term in the dynamic mass balance for ATP. I chose to define the forward direction from right to left. Similarly, the dynamic mass balance for ADP and AMP is written out. Now we move on to actual numbers. As I showed at the end of lecture 7, there are a few organs in the body that constitute maybe 7% of body mass that are responsible for over 70% of energy metabolism in the human body, and these organs include the brain, the heart, the kidney, the liver, and other digestive organs. In these tissues, the rate of ATP use is on the order of 10 millimoles per minute. Typical concentrations measured for ATP, ADP, and AMP are given. Based on these, I can calculate the energy charge, and I think 6/7 is about 0.85 or so. And with the fluxes defined and the concentrations defined, I can actually, in this case, simply calculate all the elementary rate constants based on those numbers. We call them perks for pseudo-elementary rate constants, and they are computed simply from knowing the fluxes and the concentrations. Now we move on to the subject at the heart of this class, and that is to simulate the dynamic response of this system. I am going to simulate a boundary flux, a change in a boundary flux as shown in the upper right box. I am going to instantaneously at time 0 change the numerical value of the rate constant for the use reaction by 50% and simulate the response. That response is shown in the graphs in the slide. The big graph in the background is a phase portrait of two fluxes. On the x-axis I have the rate of ATP usage, and on the y-axis I have the rate of ATP formation. The dashed diagonal line is the 45-degree line where the two are equal and the system is at equilibrium. In this case it's closed, so this is the equilibrium line. And I will open it up in subsequent slides, and this actually will be the steady state line. Above the line, the use is less than the formation rate, and below the line we have the usage rate being higher than the rate of formation. I said that the typical rate of use is 10, and so we start at the point in this plane that is 10, 10, where we have the two fluxes equal. The initial perturbation happening at T0 is a 50% increase in the usage rate. So at the beginning, the point shoots off that line to the point 15, 10, because I now have 15 millimoles per minute of usage and 10 of formation. The response on the system is simply a response that goes straight back to the equilibrium line, which is characterized by a unidimensional motion due to the mass balances that are found in this system. There is a popular way of representing the charge and the capacity pictorially as shown in this diagram, where we just draw out a box where the capacity is on the y-axis and the charge on the x-axis. In this case, there's no inflow and outflow of AMP, so the capacity is a constant, 4.2 millimolar, as calculated at the bottom of the slide, and the charge in this case drops from 0.86 to 0.78, and that was shown in the insert on the previous slide. Let me return to that briefly. In the insert here in panel B, we see that the ATP concentration drops in response to the perturbation, whereas ADP and AMP increase, and in panel C we see the transient behavior of the drop in the energy charge, just a smooth landing, as we called it in previous lecture, from to the new steady state. We will now see that there is a timescale separation in this system between a slow change in the capacity once we open up the flows of AMP relative to a faster change in the energy charge. Before we open up the system, I want to point out that in many energy transducing tissues, high energy transducing tissues, I should say, there is a buffer on the energy charge. In cardiac myocytes, in the heart, that molecule is creatine. That is a buffer molecule. It is present at a high concentration, and you can simply transfer one of the high energy bonds on ATP onto creatine to store it on creatine phosphate. It does not get used, so this is like a dead end reaction that can be reversed. So if I increase the load all of a sudden on ATP, I can dip into that buffer to enhance my ability to respond and spread it out a little bit in time. In panel B here, I show what I had before, the capacity and occupancy definitions for the adenosines. We can have exactly the same definition for the buffer, where the capacity to carry a high energy bond is simply the summation of the two concentration forms, and the occupancy would be just the charged form. So here creatine is symbolized by a gray triangle, and that red circle attached to it would be the high energy bond on it. If you wanted to, you can actually generalize the definition of capacity and occupancy as shown to the bottom right to get an overall measure for the whole system. If I perturb this system now the same way as before, I can see the energy charge dropping as before between the same levels, but at a slower rate, and the buffer charge is shown as the lower curve that also drops. In the pictorial depiction to the bottom left, I see now my adenosine capacity as before, and that is 4.2 millimolar, but on top of that I have a buffer now of 10 millimolars in the creatine pool. And if I combine them together into an aggregate energy charge, I would get the diagram on the bottom right, where I now have 14.2 millimoles capacity to carry energy. So this means that the density, the number of high energy bonds per unit volume, goes up dramatically, and I can support higher energy transduction in the tissue as a result. The change in the energy charge is the same as before, but now it's buffered, moves a little more slowly than before. So I have shown you how I carry out the first modification of my basic model. Let's now put the buffering capacity to the side again and consider opening up the system. Now I'm going to add the reactions that are associated with the influx of AMP, its formation rate, and then its drainage rate. And as shown in the mass balance, dynamic mass balance at the bottom, those terms are now non-zero. I also put in a number for the drain of 0.03 millimoles per minute, as this is the typical turnover rate of AMP in tissues. And I put the number 10 above the ATP usage rate to show you that these are 300-fold different in magnitude, and therefore I will have a fast time scale and a slow time scale in this system. The rate constant for the drain is simply the steady state concentration of AMP that I decided to be 0.1. And when that concentration is multiplied by a rate constant, it should give me 0.03, and that'll be my rate constant. Now I can carry out the exact same simulation as I did for the closed system. In panel A, I'm drawing the same diagram as before, where I look at the phase plane that has ATP usage on the x-axis and the formation rate of ATP on the y-axis. This 45-degree line that we show is now the steady state line. The simulation starts out at the point 10, 10 as before, and as I increase the usage rate by 50% initially, instantaneously, I shoot my point off that line to the point 15, 10 as I had before. The initial reaction is the rapid distribution of high energy bonds that drives me towards the steady state line. I don't quite get there, but I get very close, so close that we can't see the difference between the dashed line and the solid line in this case. But I don't get quite all the way there, and the simulation continues for a long time as AMP is being drained from the system, and I crawl slowly along the 45-degree line to the eventual steady state that is somewhere below 7 millimoles per hour. In panel B, I now add a new phase plane where I show on the x-axis the ATP usage rate, just as in panel A, but on the y-axis here, I show the drain of AMP from the system. The steady state line in this case for AMP is just at 0.03. So in this case, in this phase portrait, my simulation starts at 10, 0.03. Initially, it shoots up to 15, 0.03. And since the AMP concentration builds up during the redistribution of the high energy phosphate bonds, the drain rate actually goes up, almost doubles, almost goes to 0.06. After I reach that point, the AMP is now being removed from the system. There's more leaving than coming in, and it's siphoning off a little bit of the ADP and the ATP, and it's slow because the flux out, the net flux out is very slow, but it drops over a long period of time to roughly 7, little below 7 on the x-axis for the ATP use and 0.03 for the y-axis, because the AMP drain must match the AMP input as we reach the eventual steady state. So these two phase planes explain to me how the key fluxes are migrating during this dynamic response. I can also look at the pools that I defined before, the occupancy pool on the x-axis and the capacity on the y-axis. And as you're reminded of at the bottom of the slide, I can get a pool transformation matrix where I take the solutions for X and map them into the pools, and then I can just plot these two pools. And you can see the initial point is up in the upper right-hand corner of the phase portrait. Initially, I get a rapid, almost horizontal movement to the to the left, where the occupancy drops, but the capacity is essentially a constant because very little AMP has left the system. The panel B insert shows the response of the energy charge on that time scale, where it drops from the 0.86 to the 0.78 as it did before. Then you see a slow motion along a line with a constant slope of 0.77. The slope of this line is the energy charge, and you see in panel C the insert that has a time scale of hundreds of time units. It is basically flat. So the energy charge as a parameter is a constant, even though the occupancy and the capacity are changing notably over time. This feature of keeping the energy charge, a constant, is built into the stoichiometry of this system, and there is no need to attribute this to any regulation. So this becomes a basic mass action property of the stoichiometric matrix that describes this system, and certainly this property could be augmented by regulation, as we shall discuss in the next lecture. I can show this pictorially as before, where I have a fast drop in the energy charge as I showed before, and the capacity is a constant, and then that's followed by a slow drop in the capacity, almost in half, while the energy charge is a constant. So this two-dimensional representation of the capacity and the charge represents one useful pictorial or graphical representation of the response. I could have put a third case in here where I combine the buffer and opening of the system, and that is straightforward and in fact is relegated to a homework problem given in the text. And if you solve that, you can see the interaction between those two. What I'm going to do instead now is to proceed with this basic motif and couple it to a prototypic pathway that is making ATP. And that system is shown in the dashed red box towards the top of this slide. A prototypical pathway is such that it takes a substrate like sugar, like glucose, charges it by spending ATP to a high energy intermediate that is subsequently degraded to generate more ATPs than I spent on charging it. In this case, I am charging it with 1 ATP and I am generating 2. That increase in the ATP production over the expenditure allows me to drive a load where I transfer a phosphate group to the moiety Y. Notice that that phosphate group is the inorganic phosphate group that is incorporated in step 2, in V2 in the pathway. This is often an overlooked fact in glycolysis, namely that the incorporation of the inorganic phosphate by gap dehydrogenase is in fact a key step in glycolysis. And now I've given away which pathway I'm prototyping in this box. It turns out though that degradation of most major types of nutrients follows the same pattern. Charging in the beginning followed by recovery of metabolic energy at a higher rate than spent for charging. Now in this case I have loads of ATP use, that is V1 and the load. So the overall load is the summation of the two. And if that is a total of 10, for numerical purposes, I put the boundary flux for x1, B2 to 5. So we have now two inputs or two forcing functions, as I discussed in chapter 6, of B1, that is 0.03, the synthesis of the AMP carrier, and B2, that is 5, which is the input of the primary substrate. This is shown pictorially on the diagram below, where the metabolites is now as a circle, and that gets decorated by one high energy phosphate bond. And as it's stripped off again, a second one is incorporated, and you see pictorially that I have now two ATP moieties produced in the bottom end of the pathway, while upstream I use one. I guess one of the basic truths of this schema is that it takes energy to make energy, whereas we know in life generally it takes value to create value, it takes money to make money. I can now simulate this system to an increased load, 50% increase in the rate of use of ATP in the load reaction, just as I did before. However, in this case, that load will not be increased by 5, but by 2.5, because V1 already is 5 of the total of 10, which is the total load of on ATP. The dynamic response is shown here, and the way I calculate the kinetic constants is shown in the red box. They are just based on the fluxes, steady state fluxes, and the concentrations. Again, these are the perks or the pseudo-elementary rate constants. Let's look at the first column of graphs here. These are the transient responses. Panel A, I have just the concentrations. So ATP drops as I increase the rate of use in the load reaction. But because I have to reach a flux of 5 through V1, X1 has to go up, because V1 will be the product of X1 and X2. Product of X1 and ATP. The second reaction in the prototypic pathway will have slightly different dynamics with respect to the substrates and the products, and you see a slower long-term transient in X2 ADP and AMP that I will return to in a moment. Panel C shows the major fluxes and how they respond. The ATP load jumps from 5 to 7.5. That's the 50% increase. But because of the boundary flux number 2 being 5, the eventual steady state of this system is going to be the same flux map as we started out with. So the load has to drop to 5, and V2 and V1 also have to go to 5, which is the eventual steady state. As you see, V1 drops initially and recovers, and this is because the ATP concentration drops, whereas V2 goes up and then down. It goes up because in the beginning ADP, that is a substrate for that reaction, increases. In these dynamics, you see a mild overshoot, and then the steady state is almost reached. Panel E shows the low flux reactions, which is the drain, and since the drain operates on AMP, it wiggles the V distribution reaction that kind of tracks those concentrations because it's inherently fast, but it follows the slow drift in the reactants of that reaction. So the drain goes up from 0.03 in the beginning and then slowly starts going back down. If you look to the column of graphs on the right hand side in the blue box, we see the long-term response. Now we're talking tens of time units. You see X1 and ATP have kind of reached a steady state early on. X2 continues to build up over time, while ADP and AMP are dropping on this longer time scale because AMP is being drained from the system to a level where the flux reaches 0.03. Panel D shows the initial reaction in the major fluxes that then go very close to 5 but not quite. And then panel F shows the slow or the long-term changes in the drain flux as it asymptotically approaches 0.03. So these are the primary transients as viewed by time profiles of concentrations and fluxes. We can now show this on a phase plane similar to the one that we had before. We have a 45-degree line, the steady state line, where we start out at the point 10, 10. We increase the drain flux by 50%, which does not take us out to 15, but 12.5 in this case, because the load flux is 5. So we shoot out to 12.5. The initial reaction is to try to move back to the steady state line, but it doesn't quite get there. It turns around, moves parallel to the steady state line, overshoots the steady state a little bit, returns and comes to the eventual steady state, which is the same as the original one. This is different from the system that we showed before, and those differences are due to boundary flux number 2. You see in the little insert, panel B, the energy charge. It starts out high here at 0.86 as before, and then it drops down initially, but on the slow time scale, it actually recovers. So this is called a rejection property. There is a disturbance, and the system counteracts it after a while and tries to overcome that disturbance as it reaches the original steady state. This is built into the stoichiometry and the constancy of the boundary fluxes. Panel C has the ATP workload on the x-axis and the AMP drain on the y-axis as before. We start out at the point 10,0.03 as before, shoot up to the point 12.5, 0.03 as the initial state, and as the load goes down, the drain shoots up, and that reaches an apex, and then it turns around and starts dropping almost vertically when the load is close to 10, and it eventually reaches the same steady state as it started at. Now here we have the module coupled to a pathway. It's not uncoupled as in the original example. The pathway input flux is fixed, and therefore some of the fluxes are fixed. The flux map must return to the original steady state, but the concentrations will not, because the rate constant, one of them has changed, and that imbalances the concentration values in the steady state. So that is the consequence of increasing the rate of use of ATP by 50%. Not the absolute amount, but the rate of use. We changed the rate constant. So in this lecture, there are a few important lessons. First, the bilinear properties of biochemical reactions can lead to complex patterns of exchanges of key chemical moieties and other properties like redox potential. And these are carried by carrier molecules, coenzymes or cofactors, different names for these so-called side reactants in the primary metabolic reactions. When you look at the cofactor view of the network, you see a tangle of cycles around which the function of the whole integrated network is oriented. It's not so much about individual pathways, but how the different properties travel through these cofactor pools onto their eventual acceptors. We've seen that we can build scaffold or skeleton dynamic models by simply using dynamic mass balances, writing in elementary representation and mass action kinetics of the reactions using the reactants and the products. So these are simulations in here are simply based on mass action kinetics on top of this scaffold, the stoichiometric scaffold, and some dynamic properties are built into the scaffold, and the one that is notably highlighted in this lecture is the recovery of the energy charge with the challenge it was faced with when the basic motif of adenosine nucleotides was coupled to a pathway. We also saw that complex kinetic models are best built in a bottom-up fashion where you start with some core process and add to it more and more complexity in a stepwise fashion. And by simulating responses at each step, we understand the function of each module as we add it and how it changes the dynamic properties of the system. We will do this extensively in subsequent lectures and chapters in the book. Once we formed a dynamic network model of a network, the perturbations that we are interested in are normally in the boundary fluxes. In this case, we focused on the demand flux of ATP and changed the rate of use of ATP, and that is something that is forced on the system. A reoccurring theme in this simulation is the formation of pools and the state of those pools, namely the distribution of the members of the pools. What is the relative concentration of each? We will see this over and over again, not only for cofactor pools, but pools of protein. A protein that isn't synthesized or degraded is total in its overall amount, but the states in which that protein is, bound or free, phosphorylated, not phosphorylated, and so forth, varies. So the fraction of the pool that is in a particular state becomes an important variable. For the cofactors, we think of those as charges, as in the energy charge, with an analogy to a battery. As we add modules to a network and build it in complexity, we see the multi-timescale feature appear. And this happens in almost every complex model that you will build. Again, in part 1 of these lectures, we had the liberty to pick numerical values for the rate constants. When you deal with real systems, you do not. And we talked about that in lecture 7. and what the typical numerical values are. In here, we saw a timescale hierarchy form based on the rate of use of ATP and the rate of turnover of the AMP molecule, that is the key carrier in this case, the blue box as I depicted it. So now you're introduced to building kinetic models up in a stepwise fashion based on a stoichiometric scaffold and the calculation of perks based on what you know about the concentrations in the system and the fluxes through it. We will, in lecture 9, move on to the incorporation of regulatory features in networks, and they are also approached in this modular fashion by adding a regulatory module that is known to a different reaction in the stoichiometric scaffold that represents the whole network. This completes the lecture.